Hello and welcome to this video summary of our work from voxels to pixels and back, self-supervision in natural image reconstruction from fMRI, to be published at NeurIPS 2019. I'm Guy Gaziv, PhD candidate from the Mihaly Rani Lab at the Weizmann Institute of Science, and I'm going to walk you through the main contributions and results from this paper. In this work, we demonstrate highly accurate reconstructions of images observed by a subject, using nothing but his recorded brain activity, captured via fMRI. We achieve this for two very different fMRI datasets using a novel self-supervised method. The available data for the task consists of about 1,000 pairs of images and their corresponding fMRI scans. Traditionally, this paired or labeled data is used to learn the mapping between the visual stimuli and their brain activity representation. However, since the data is limited and cannot span the huge space of natural images and natural fMRI samples, such decoders are prone to poor generalization to new held-out data. We propose to put back-to-back an encoder model which maps images to their fMRI and a decoder model which captures the inverse mapping. The following training configuration imposes that images return to themselves under transformation ED, Encoder-Decoder. This enables to train on additional data of any unlabeled images. Those can be images for which we don't have an fMRI recording at all. In our case, we used additional 50,000 natural images from ImageNet validation set. This introduces adaptation to the statistics of natural images. Moreover, we can also cascade the encoder and the decoder the other way around, imposing that unlabeled fMRI samples are mapped to themselves under transformation decoder-encoder, DE. Once again, you have the liberty to choose here your unlabeled data to train on. Importantly, our approach encourages to use here the unlabeled fMRI samples from the test data, but without using any of their corresponding images. Since those images are never used in training, it is perfectly legal to train on those test fMRI samples, which are just the samples from the decoder's input space. Importantly, this training configuration adapts the decoder to the statistics of your test fMRI data. This is the main performance gain factor of our method. We conduct training in two phases. In the first phase, we train the encoder alone in a supervised way. This enables the encoder to converge first and serve as strong guidance for the decoder, which is trained next. In the second phase, the encoder's weights are fixed, and we train the decoder on 3 objectives simultaneously within each single batch. These objectives include supervised training on labeled training data, unsupervised training on unlabeled natural images, and unsupervised training on unlabeled test fMRI data. Let's see the effects of each of these components on the test reconstructions. So these are 5 test images, never used in training. This is what we get when we employ the decoder supervised training alone. One can observe that the reconstructions are quite blurry. Adding the training on unlabeled images indeed introduces some 1/f natural image statistics. However, the main leap appears when adding the training on unlabeled test fMRI. This highlights the importance of training on the input test data, here the unlabeled test fMRI. Adaptation to test data makes our method reconstruct impressively not only a selected few test examples, but many of them, all of which are included in the paper. In addition, our method is also easily applied to other very different fMRI datasets under the same configuration and hyperparameters. We also favorably compete against GAN-based methods, which oftentimes produce natural-looking images, but not as faithful as ours to the underlying fMRI and its corresponding ground truth image. Log on to our project website for more information about the project. I'm Guy Gaziv, and thank you for watching.